In the rolling hills of southern England, massive stones stand in perfect formation against the gray morning sky. Each monolith weighs more than 50 tons. Some tower 20 feet into the air. They were placed with mathematical precision thousands of years before the invention of the wheel. Before metal tools, before written language even existed. The people who built Stonehenge had nothing but their bare hands, crude stone implements, and an inexplicable understanding of engineering that defies everything we thought we knew about our ancestors. But Stonehenge is just the beginning. Across the globe, from the windswept plains of Easter Island to the dense jungles of Peru, ancient civilizations somehow managed to move stone so massive that even today's construction crews would struggle with the task. We're talking about blocks weighing hundreds of tons transported across impossible terrain, lifted to dizzying heights, and positioned with laser-like accuracy. The Egyptians hauled 2-million-pound granite obelisks from quarries hundreds of miles away. The builders of Machu Picchu somehow carried 15-ton blocks up nearly vertical mountain faces. On Easter Island, nearly 900 enormous statues were mysteriously moved from a central quarry to positions scattered across the entire island. How is this even possible? How did our Stone Age ancestors accomplish feats that would challenge modern engineering? And more importantly, what ingenious methods did they develop that we've completely forgotten? For decades, archaeologists dismissed these achievements with vague explanations about ramps, ropes, and countless workers. But recent discoveries are revealing something far more extraordinary. Our ancestors weren't just strong and determined. They were brilliant engineers who developed sophisticated techniques that were lost to time. What we're about to uncover will completely change how you think about ancient civilizations and human ingenuity itself. The mystery begins with a simple but haunting question that has puzzled researchers for generations. When you stand before these ancient monuments, you can't help but feel small. The sheer scale is overwhelming. But it's not just the size impressive, it's the precision. These aren't crude piles of rocks thrown together by primitive people. They're masterworks of engineering planned with mathematical accuracy and executed with flawless technique. Take the Great Pyramid of Giza. This isn't just a big pile of stones, it's composed of over 2 million individual blocks, each weighing between 2 and 15 tons. The pyramid's base covers 13 acres and was originally 481 feet tall. The alignment is so precise that it's oriented to true north within just 3/60 of a degree. The blocks fit together so perfectly that you can't slide a knife blade between them. And all of this was accomplished by people who supposedly had no advanced technology. But here's where it gets really interesting. Recent archaeological evidence is revealing that our Stone Age ancestors were far more sophisticated than we ever imagined. They weren't the grunting cavemen depicted in old textbooks. They were innovative problem solvers who developed ingenious solutions to seemingly impossible challenges. The first clue comes from understanding what tools these ancient builders actually had at their disposal. Forget everything you think you know about primitive technology. While they didn't have steel or machinery, stone developed remarkably effective age people's implements. They create hard, incredibly stone tools by carefully selecting specific types of rock. Obsidian blades could be sharper than modern lapels. Granite surgical-esque hammers could shape the hardest stones with surprising precision. But the real breakthrough came when archaeologists started paying attention to something that had been hiding in plain sight for centuries. All around these ancient monuments, researchers began finding strange grooves carved into solid rock. These weren't decorative patterns or random scratches. They were systematic channels, perfectly shaped and positioned with obvious purpose. What were these mysterious grooves used for? The answer would revolutionize our understanding of ancient engineering. These grooves were part of an elaborate system that allowed Stone Age builders to manipulate massive stones with minimal effort. By carving precisely angled channels and using a combination of leverage, friction, and ingenious mechanical principles, ancient engineers could move blocks that weighed many times more than what their muscle power alone could handle. Archaeological experiments have recreated these techniques with stunning success. Small teams of people using only Stone Age tools have successfully moved multi-ton blocks across considerable distances. The secret lies not in brute force, but in understanding physics principles that we thought weren't discovered until thousands of years later. One of the most remarkable examples comes from Easter Island, where researchers finally solved the mystery of how the massive statues were transported. For generations, archaeologists assumed the moai were somehow rolled or dragged across the island. But oral traditions among the Rapa Nui people told a different story. They insisted the statues had walked to their final positions. This seemed like decide obvious mythology until researchers to test the idea literally. They discovered that the statues were designed with a forward-leaning center of gravity. By attaching ropes in specific positions and using a carefully coordinated rocking motion, small teams could actually make the massive statues walk upright across the landscape. The statues weren't transported lying down. They moved standing up, swaying from side to side in a rhythmic dance across the island. This discovery opened up an entirely new way of thinking about ancient engineering. Our ancestors weren't just using crude force to overcome massive obstacles. They were developing elegant solutions based on sophisticated understanding of physics, leverage, and mechanical advantage. The evidence keeps mounting from sites around the world. In Peru, researchers have found that the massive stones of Sacsayhuaman weren't just placed randomly. They were positioned using a complex system of precisely calculated angles and counterweights. Each stone was shaped to fit perfectly with its neighbors, creating structures so stable they've survived hundreds of earthquakes that destroyed more recent buildings. In England, new analysis of Stonehenge reveals that the massive trill blocks stacked on top of each other. They were engineered as integrated units, with Athons weren't just heavy horizontal stones actually locked into place using sophisticated joinery techniques. The builders carved precise mortise and tenon joints, just like a master carpenter would use, but working with stones weighing dozens of tons. Perhaps most remarkably, these techniques weren't limited to famous monuments. Archaeological surveys are revealing that Stone Age peoples routinely moved massive stones for everyday construction projects. Entire cities were built using blocks that would challenge modern equipment. This wasn't occasional heroic effort, this was standard construction practice. But how did they develop these techniques? How did Stone Age peoples figure out complex engineering principles without written language, mathematical notation, or scientific instruments? The answer lies in something that modern society has largely lost: the accumulated wisdom of oral tradition and hands-on experimentation passed down through countless generations. What emerges from this evidence is a picture of our ancestors that's completely different from traditional assumptions. These weren't primitive people struggling against impossible odds. They were skilled professionals who had mastered complex technologies perfectly suited to their materials and environment. They developed solutions that were often more elegant and efficient than modern approaches to the same problems. The sophistication of these ancient techniques becomes even more apparent when we examine the logistics behind major construction projects. Moving a single massive stone wasn't just a matter of muscle power and determination. It required careful planning, resource management, and coordination that would impress modern project managers. Consider the sheer scale of organization required. Archaeological evidence suggests that major stone-moving operations involved hundreds or even thousands of workers, each with specialized roles. There were quarry specialists who understood exactly how to extract blocks without damaging them. Transport teams knew the optimal routes and techniques for moving stones across different types of terrain. Positioning experts could maneuver multi-ton blocks into precise locations with millimeter accuracy. But perhaps most remarkably, these operations had to be sustained over decades or even centuries. The Great Pyramid wasn't built in a few months. It required consistent effort over approximately 20 years. This means ancient societies had developed systems for maintaining institutional knowledge, training new workers, and ensuring quality control across multiple generations of craftsmen. Recent archaeological discoveries are revealing the incredible attention to detail that went into these projects. At Pumapunku in Bolivia, researchers have found stone blocks cut with such precision that the edges are straight to within fractions of an inch. The surfaces are so smooth and flat that they rival modern machine work. This level of accuracy wasn't achieved by accident. It required sophisticated measuring techniques, quality control systems, and master craftsmen who understood their materials with scientific precision. The tools themselves tell fascinating stories about ancient innovation. While they developed, Stone Age peoples didn't have metal implements, incredibly effective alternatives. Copper tools, while relatively soft, could be hardened through specific techniques that allowed them to cut granite. Stone hammers were shaped with mathematical precision to deliver maximum force while minimizing effort. Wooden levers were engineered with specific length ratios to provide optimal mechanical advantage. One of the most intriguing discoveries involves the use of sound and resonance. Archaeological experiments have shown that ancient builders could determine the internal structure of stones by listening to the sounds they made when struck with hammers. Experienced workers could identify internal flaws, stress points, and optimal cutting locations just by analyzing acoustic feedback. This technique allowed them to work with massive stones without risking catastrophic failures that could destroy months of effort. The transportation methods reveal equally sophisticated understanding of physics and engineering. Ancient builders didn't just drag stones across the ground. They developed elaborate systems of rollers, tracks, and mechanical devices that distributed weight and reduced friction. Archaeological evidence shows wooden trackways built specifically for heavy transport, with precisely spaced supports and carefully engineered curves that allowed teams to maintain momentum even when changing direction. Some of the most impressive innovations involved water-based transport. Ancient engineers understood that floating stones on rivers or constructed waterways could dramatically reduce the effort required for long-distance movement. They built elaborate canal systems, constructed specialized barges, and developed techniques for loading and unloading massive blocks without modern cranes or lifting equipment. But the real revelation came from analyzing wear patterns on ancient tools. These marks tell stories of specialized techniques passed down through generations of master craftsmen. Different types of wear indicate specific motions, pressures, and applications. Some tools show evidence of being used for rough shaping. Others display the microscopic signatures of precision finishing work. The sophistication of these specialized applications suggests workshop systems as organized as modern manufacturing facilities. Archaeological excavations at ancient quarry sites reveal the true scope of these operations. What appeared to be simple stone extraction points were actually complex industrial facilities. Workers had developed systematic approaches to every aspect of stone processing. They understood geological formations well enough to predict exactly where the best building materials could be found. They knew how different rock layers would behave under various extraction techniques. The quarrying process itself demonstrates remarkable geological knowledge. Ancient workers could identify internal stress patterns in solid rock. They knew exactly where to place their tools to split stones along predetermined lines. Fire-setting techniques allowed them to crack massive rocks with surgical precision. By building controlled fires against stone faces and then rapidly cooling them with water, they could fracture rocks exactly where they wanted without damaging surrounding material. Wooden wedge systems reveal equally sophisticated understanding of material science. These weren't random pieces of wood jammed into cracks. They were precisely shaped implements made from specific tree species, selected for their expansion properties. When soaked with water, these wedges would swell with tremendous force, splitting rocks along carefully planned fracture lines. The technique required understanding wood grain patterns, moisture absorption rates, and expansion pressures that rivals modern engineering knowledge. The evidence for advanced planning becomes even more compelling when we examine the logistics of major construction projects. Recent archaeological surveys have mapped extensive networks of ancient roads built specifically for stone transport. These weren't simple dirt paths. They were engineered transportation systems with calculated grades, proper drainage, and strategically positioned way stations. Ground-penetrating radar has revealed the sophisticated construction of these ancient roadways. Multiple layers of carefully selected materials created surfaces capable of supporting enormous loads. Foundation layers used large stones for stability. Intermediate layers employed progressively smaller materials to create smooth load distribution. Surface layers were often paved with precisely fitted stones that provided optimal traction for heavy transport operations. The way stations positioned along these routes tell fascinating stories about ancient project management. These weren't random rest stops. They were carefully planned facilities positioned at mathematically calculated intervals. Each station provided specific services needed for long-distance stone transport. Some offered tool maintenance facilities, others had specialized equipment for adjusting loads or changing transport methods. The most elaborate stations included workshops for repairing transport equipment and housing for specialized workers. Archaeological analysis of these sites reveals standardized construction techniques used across vast geographic areas. The same engineering principles appear at sites separated by thousands of miles and hundreds of years. This suggests sophisticated knowledge transfer systems that could preserve and disseminate technical information across ancient civilizations. Trade networks weren't just moving goods. They were sharing engineering knowledge and construction techniques. The transport vehicles themselves demonstrate remarkable innovation. Wooden sledges found at various archaeological sites show engineering sophistication that challenges assumptions about ancient technology. These weren't crude sleds dragged across rough ground. They were precision-built vehicles designed for specific load capacities and terrain conditions. Runner angles were calculated for optimal weight distribution. Surface treatments reduced friction. Rope attachment points were positioned for maximum mechanical advantage. Some of the most intriguing discoveries involve specialized stone-moving equipment that has no modern equivalent. Archaeological sites have yielded wooden devices with complex gear ratios created entirely from organic materials. These machines used combinations of levers, pulleys, and rotating elements to multiply human effort by factors of 10 or more. The engineering principles involved demonstrate understanding of mechanical advantage that wasn't supposed to exist for thousands more years. Recent experimental archaeology has successfully recreated many of these ancient machines. Using only materials and techniques available to Stone Age peoples, modern researchers have built functioning devices capable of moving multi-ton loads with surprisingly small crews. The key insight is that ancient engineers weren't limited by lack of metal or modern materials. They developed alternative approaches that were often more elegant than contemporary solutions. The precision positioning techniques reveal perhaps the most sophisticated aspect of ancient stone-moving technology. Getting massive blocks to construction sites was challenging enough. Placing them in exact positions with millimeter accuracy required engineering skills that rival modern capabilities. Archaeological evidence shows that ancient builders developed ingenious methods for fine-tuning stone placement that have been completely forgotten by modern construction. Sand-based adjustment systems allowed for incredibly precise positioning. By placing stones on carefully constructed sand platforms, builders could make minute adjustments to alignment and elevation. As sand was systematically removed from specific areas, massive stones would settle into exactly the required positions. This technique provided precision control that would be difficult to achieve even with modern hydraulic systems. counterweight mechanisms discovered at various sites show equally sophisticated understanding of balance and leverage. Ancient engineers could lift and position massive stones using elaborate systems of weights and pulleys created entirely from stone, wood, and rope. These systems distributed lifting forces across multiple points, allowing relatively small teams to manipulate enormous loads with precise control. The mathematical precision evident in ancient construction reveals scientific thinking that challenges traditional timelines of human intellectual development. Stone blocks at various sites show evidence of being shaped using geometric principles that weren't supposed to be discovered until classical antiquity. Angles, proportions, and dimensional relationships demonstrate systematic application of mathematical concepts. Measurement systems used by ancient builders show standardization across vast geographic areas. The same dimensional units appear at sites separated by thousands of miles, suggesting sophisticated communication networks and shared technical standards. These weren't arbitrary measurements. They were carefully calculated standards that optimized construction efficiency and structural performance. The environmental adaptation evident in these regional variations demonstrates systematic thinking about the relationship between construction methods and natural systems. Builders in different regions developed techniques that worked with local environmental conditions rather than fighting against them. This approach produced structures that lasted longer and required less maintenance while minimizing ecological disruption. Technological evolution visible across different time periods shows continuous innovation and improvement in stone-moving techniques. Early methods were refined through practical experience and systematic experimentation. Later developments incorporated lessons learned from previous projects while introducing new innovations that enhanced efficiency and effectiveness. The acceleration of technological development evident in archaeological sequences suggests systematic research and development processes that deliberately sought to improve existing methods. Ancient engineers weren't content with techniques that merely worked. They continuously refined their approaches to achieve better results with less effort and greater reliability. Cross-cultural exchanges evident in construction techniques reveal international networks that shared engineering knowledge across different civilizations. Similar innovations appearing simultaneously in widely separated regions suggest active communication and technology transfer between different cultures. These exchanges accelerated technological development and spread best practices throughout the ancient world. This acoustic testing wasn't random experimentation. It was systematic application of scientific principles that allowed builders to evaluate materials with precision that rivals modern ultrasonic testing. Master craftsmen developed such acute hearing that they could identify subtle variations in stone density, internal stress patterns, and hidden fractures just by listening to acoustic feedback. The implications are staggering. Every massive stone in ancient monuments had been individually tested and approved using Ian's techniques that read optimal performance. This explains why structures built thousands of years ago continue to stand while modern buildings begin deteriorating within decades. Stone Age builders weren't just moving big rocks. They were selecting and positioning precision-engineered building components. Archaeological analysis of construction sites reveals that ancient builders had developed sophisticated understanding of geological formations that guided their quarrying operations. They knew exactly which rock layers would provide the best building materials. They understood how different geological conditions affected stone quality and workability. They could predict how stones would behave during extraction, transport, and construction based on their geological origins. This geological knowledge extended to understanding how different stone types would interact when used together in construction. Ancient builders knew which combinations would create stable structures and which would lead to problems over time. They understood expansion and contraction rates, weathering patterns, and compatibility issues that could affect long-term structural integrity.